goal of this unit is to understand how a compressible fluid responds to changes in the area it's flowing through, such as those encountered by a gas being exhausted through a nozzle. To simplify our analysis of flow with area change, we need to make some assumptions. In a real flow through a variable area duct, such as the one shown in the top figure, the flow will not be uniformly aligned with the center line of the duct. The velocity will also drop to zero at the walls due to the presence of viscous boundary layers. However, if we assume a gradual area change and that the boundary layers are thin enough that we can neglect viscous effects on the mean flow, then we can reasonably approximate the velocity profile as being uniform across the duct, as shown in the bottom figure. Under these assumptions, the flow only varies in the x direction along the duct, so it's called quasi-one-dimensional. Also, as we've neglected viscous losses, we can assume the flow is isentropic as long as no shock waves appear. Finally, we assume the flow to be steady. To begin our exploration of flow with area change, we start with conservation of mass, which is also known as the continuity equation. For a steady, quasi-one-dimensional flow, this tells us that the mass flow rate, which is given by the product of the fluid density ρ, the velocity v, and the duct cross-sectional area A, is constant. Differentiating this expression using the chain rule, we find that VA times dρ plus ρA times dV plus ρV times dA is equal to 0. If we divide through by ρVA, we obtain a very revealing form of the continuity equation. dρ on ρ plus dV on V plus dA on A is equal to 0, which we label equation 1. These relative changes in quantities are known as dilatations. Equation 1 tells us that these dilatations in these three quantities must sum to 0 in order for mass to be conserved. For an incompressible flow, where there's no change in density, so dρ on ρ is equal to 0, this means that a relative change in velocity must always be equal and opposite to the relative change in area. So a decrease in area results in an increase in speed, as we know intuitively from our everyday experiences. For compressible flows, however, dρ is not 0, so there are many more ways for conservation of mass to be satisfied. A large negative change in area could be balanced by moderate increases in both density and velocity, or by a large increase in density and a small decrease in velocity, or vice versa. To find out which of these really occur when the flow is compressible, we need to analyse this quasi-one-dimensional flow further. So the objective of this analysis is to determine how each of the flow quantities responds to a change in area. During the analysis, we'll keep track of the important equations we'll derive here on the right. Let's begin by applying conservation of energy. Because this flow is adiabatic, the stagnation enthalpy, H0, which is equal to H plus 1/2 V squared, is going to be equal to a constant. Okay, we're dealing with the differential forms of the equations, so let's take the derivative of this expression, and we get that dH plus VdV is equal to 0. Now we're going to make use of an intermediate result that we got when we were deriving the isentropic flow relations. This was first derived by Gibbs, and he found that TdS is equal to dH minus dP over ρ. Because we're dealing with an isentropic flow in this case, ds is going to be equal to 0, and this just tells us that the change in enthalpy, dH, is equal to dP over ρ. If we then use this to replace dH in our differential form of conservation of energy, then we're going to end up with dP over ρ plus VdV is equal to 0, and we'll label this equation 2. Now this is a very interesting and useful result. What it tells us is that the change in pressure must always have the opposite sign of the change in velocity. And this is in line with our intuition and experience from incompressible flows, where if you have a flow from a high pressure to a low pressure region, you expect that flow to accelerate. So let's transfer this intermediate result over to our column of key equations. What we'd really like to do in order to express the change in velocity in terms of the change in area is to eliminate density from this relation. So we really need the change in density in terms of the change in velocity. Now we just derived an expression relating the change in pressure to the change in velocity, so all we really need to do is to relate the changes in density and pressure. And one way we can do this for this isentropic flow is from the definition of the speed of sound, which is a squared equals del p del rho at constant entropy. Now because our flow is already isentropic, this tells us that dp is equal to a squared d rho. If we use this in equation 2, so we're using it here to replace dp, what we're going to end up with is a squared d rho on rho plus v dv is equal to 0. So let's divide both sides by a squared. So then we're going to get d rho on rho plus v on a squared dv is equal to 0. So let's both multiply and divide by v, and then what we should see is that this here is just equal to the Mach number squared. So what we have ended up with is d rho on rho is equal to minus m squared dv on v. Now this we're going to label equation 3, and this is really starting to tell us something about the nature of compressible flow, and this is going to be extremely useful in understanding why the behavior of compressible flow changes so remarkably at certain key breakpoints. So what this is really telling us is that for subsonic flows where m squared is less than 1, the density dilatation is going to be much smaller than the velocity dilatation, and the reverse is going to be true for supersonic flows. It's also the case that the density and velocity always have to change in opposite directions. So when a flow accelerates and the velocity increases, dv is greater than 0, then the density has to decrease, so d rho is less than 0. So let's transfer equation 3 to the list of key equations and move on. Now let's use equation 3 to eliminate the density dilatation from our differential form of conservation of mass. So doing this, what we get is that minus dv on v by m squared plus dv on v plus dA over A is equal to 0. So let's collect all the dv on v terms, so we can get 1 minus m squared dv over v, and let's take the area term to the other side, so it's going to become minus dA on A on the right hand side. And then finally let's just divide through by the 1 minus m squared. So what we're going to end up with is dv on v is equal to minus 1 over 1 minus m squared by dA on A. So now we've achieved our objective. We found out how one of the variables changes by itself as the area changes. We can also combine this result, which we'll label equation 4, with equation 2 in order to determine how the pressure changes. So if we do this, what we end up with is dp on rho v squared is equal to 1 on 1 minus m squared dA on A, which we're going to label equation 5. So these are both really significant results and really what we've been after for the whole analysis. And what these are telling us, which is extremely significant, is that the response of the flow in terms of these two variables to a change in area depends on whether this term 1 minus m squared is positive or negative. So this term changes signs when the Mach number is equal to 1. So that means we're going to get different responses of the flow depending on whether the flow is subsonic or supersonic. And this is what leads to some of those counterintuitive results that we get for compressible flow. So in the next unit, what we're going to do is go through how these relations affect what a nozzle does.